Hello everyone. Today we are going to study the noise in continuous wave modulation systems. Right. In earlier chapters, we studied what is continuous modulation, like amplitude modulation or angle modulation. Correct. To undertake the analysis of noise in continuous modulation system, we need to do a number of things. Like first and foremost, we must have a receiver model. Receiver model. Correct. In such a receiver, the noise is assumed to be additive. In such a receiver, the noise is assumed to be additive, white, and Gaussian. This kind of noise is known as AWGN, additive white Gaussian noise. Before proceeding to the chapter, we must be aware of few things, like what is the power spectral density of a AWGN. Suppose I am denoting the power spectral density of AWGN by N0 by 2. Right? It is denoted by Sn of F. Power spectral density is denoted by capital S subscript N. Described is the noise spectral density, and in bracket it is F. It means it is with respect to frequency. Right? This is a wideband noise. This is a wideband noise. When this wideband noise is passed through a filter, when this wideband noise is passed through a filter, it becomes a narrowband noise. And the narrowband noise can be expressed in terms of in-phase quadrature and quadrature components. The noise narrowband noise N of t can be expressed as Ni of t cos omega ct minus Nq of t sin omega ct. Whereas the power spectral density of in-phase and quadrature component of noise, that is Ni of t and Nq of t, are equal, and it is given by Sn f minus fc plus Sn f plus fc, where f is varying from minus b by 2 to b by 2, where b is the bandwidth of the filter through which narrowband noise is passed. The total bandwidth is b, from minus b by 2 to plus b by 2. The next thing we should know is that power spectral density, when a noise is passed through any linear system and we get some output, so the power spectral density of output, that is N0 of f, is equals to HF mode square into power spectral density of input. Right? Now we will switch to the receiver model. Now our first and foremost topic is we should have a receiver model. The idea of modeling is fundamental to the study of all physical systems, including communication system. Through modeling, we improve our understanding of capabilities and limitations of the systems. In formulating a receiver model for the study of noise in continuous wave modulation system, we need to keep the following points in mind. The first thing is the model provides an adequate description to form the receiver noise that is of common concern. The model accounts for the inherent filtering and modulation characteristics of the system. The model is simple enough for statistical analysis of the system to be possible. The receiver model is shown here in the picture. Here, this in this figure, this S of t represents my modulated signal which we are receiving. Right? W of t is a white noise which is being added to the modulated signal. When the signal reaches to the front end of the receiver, it becomes S of t plus W of t. That means the receiver is receiving the modulated signal and a white noise. Then we pass this signal through a band pass filter. The output of the band pass filter is represented with x of t, and x of t is nothing but s of t, that is band pass filter is passing my modulated signal without any distortion, plus it it is narrowing this white noise, that is a wideband noise, to a narrow band noise represented with n of t. Then this signal is passed through demodulator. Demodulator may be for amplitude modulation or frequency modulation depending on the which modulation scheme was used at the transmitter end. Then the output we received a signal y of t which is equals to the original demodulated signal with some noise. We have to analyze this thing. As the noise n of t here is a narrowband noise and it can be expressed in terms of quadrature components. Few things we must know about the receiver characteristics. One is the signal to noise ratio. The signal to noise ratio is the ratio of the signal power to the noise power. When I am writing signal to noise ratio at the input, this means that I am calculating signal power at the input to the noise power at the input of the receiver. Signal to noise ratio at the output means I am calculating signal power at the output to the noise power at the output. The next important parameter is figure of merit. The figure of merit is the ratio of the signal to noise ratio at the output to the signal to noise ratio at the input. Here I am assuming that my band pass filter has a bandwidth of B with the center frequency of Fc. And we must remember that in case of AM, either in DSBSC or full carrier, the bandwidth is twice of FM. So I am ending my topic here today. In the next video, I will share the effect of noise in DSP-SC receiver and AM receiver. I hope you will like this video. Bye.